Next derivation, design of cooling tubes. There are three modes of heat transfer. One is conduction, convection and radiation. But remember, a transformer uses two mode of heat transfer. One is radiation and another is convection. It has been estimated that natural cooling by a plain tank surface of transformer dissipates the losses of 6 watt per meter square per degree centigrade rise in temperature by radiation and 6.5 watt per meter square per degree centigrade rise in temperature by convection. Therefore, the total losses dissipated by plain tank is 6 plus 6.5, that is 12.5 watts per meter square per degree centigrade rise in temperature. If St is surface area of plain tank in meter square and theta b temperature rise in degrees, therefore the total loss dissipated by plain tank without cooling tubes is given as 12.5 into St into theta watts. Call this as equation number 1. From the equation 1 I can write temperature rise theta is equal to total loss divided by 12.5 St. Call this as equation 2. Now let us understand how we got this total loss dissipated as 12.5 St theta. You can see here this is a transformer, how practically how it looks like. Now I have shown you here one small square box of size 1 meter by 1 meter. So it means what? The transformer, whenever it is heated up, whenever it is gaining temperature, it will dissipate heat from its body to the surrounding by two ways. One is radiation and another is convection. So here by radiation it is going to emit 6 watts per meter square per degree centigrade rise in temperature. Similarly, by convection it is going to dissipate 6.5 watt per meter square per degree Celsius rise in temperature. Now let us say St is the total surface area of this transformer. Therefore, whenever there is an increase in temperature, the transformer is going to dissipate heat energy to the surrounding by two ways, that is radiation and convection. In total, it is going to dissipate 12.5 watts per meter square per degree rise in temperature. So this I can write the total heat loss occurring from a transformer as total loss is equal to 12.5 into total surface area into rise in temperature, that is theta. Let us continue. Now let us assume that we have added some cooling tubes to the transformer. Therefore, it improves heat dissipation by convection by 35%. Therefore, after adding cooling tubes, the convection process will improve by 35%. Therefore, losses dissipated by tubes can be given as 1.35 into 6.5 watt per meter square per degree Celsius, which is nothing but 8.8 watt per meter square per degree Celsius. Let us see how we got this 8.8 watts. We know that by convection the heat dissipated is 6.5 watt per meter square per degree centigrade. After adding cooling tubes, it is improving 35%. So now I can write the above equation as 6.5 plus 35% of 6.5. So which is nothing but, after solving, we are going to get it as 8.775, which is nothing but 8.8 watt per meter square per meter square per degree Celsius. This, in short, I can write 135%, which is nothing but 1.35 times 6.5. So you'll get the same answer, that is 8.8. Similarly, let us say by adding cooling tube, there is 40% improvement in convection. In that case, directly multiply 1.4 into 6.5, you will get it as 9.1. Similarly, if improvement is 45%, then multiply 1.45 into 6.5. Let us continue. Let us assume that AT is the total surface area of all cooling tubes in meter square, and theta is temperature rise in degrees. Therefore, the total losses dissipated by cooling tubes is given as 8.88 AT into theta. Call this as equation number 3. Let us understand how we got this 8.88 AT into theta. As we can see, we have added some cooling tubes here, and I said you that after adding cooling tubes to the transformer, its convection process improves by 35%. It means now these cooling tubes are dissipating heat at 8.88 watts per meter square per degree Celsius to the surrounding. Therefore, the total loss occurring at cooling tubes can be given as the total surface area of these cooling tubes into 8.88 into rise in temperature. So here you can see that LT is nothing but the length of cooling tube and DT is nothing but the diameter of cooling tube. So the surface area can be given as pi dl. So I can write it as the total losses occurring due to this cooling tubes as 8.88 into AT into theta. Let us continue. Therefore, the total losses dissipated by tank and tube is given as capital W is equal to 12.5 St theta plus 8.88 AT theta. From the above equation, by rearranging the terms, we can calculate surface area of all tubes AT as 1 by 8.8 theta into the bracket W minus 12.5 St theta. After simplifying, we will get it as 1 by 8.8 into the bracket W by theta minus 12.5 St. Call this as equation number 4. As I have already told you, dt is nothing but diameter of cooling tube in meters and lt is length of cooling tube in meters. Therefore, surface area of one cooling tube can be given as AT1 is equal to pi dt into LT. Call this as equation number 5. Therefore, the total number of cooling tubes, capital N, can be calculated as ratio of surface area of all cooling tubes divided by surface area of one cooling tube. I can write this one as capital N is equal to AT by AT1. After substituting the value of AT and AT1, we will get the above equation as 1 by 8.88 pi dt LT into the bracket W by theta minus 12.5 St. Here are few important notes for your consideration. Remember, if in numerical the diameter of cooling tube is not given, you have to assume it as 5 cm and length of cooling tube as 90% of height of tank and spacing between tubes as 7.5 cm. And remember, The top view gives the information about width and breadth of the transformer tank. The transformer frame dimensions. For single phase core type transformer, this is the diagram. You can see DOHV is nothing but outer diameter of HV winding. Now this capital D is nothing but distance between center to center limb, and here this is the midpoint, so I am writing this length as DOHV by 2. So if you write down, the total height of the transformer is given as HW plus 2HY, WTR as capital D plus DOHV by 2 plus DOHV by 2. So in total it is WTR is equal to D plus DOHV. Then next BTR is equal to, that is breadth of transformer is equal to DOHV. Similarly for 3-phase core type transformer, you can write HTR is equal to HW plus 2HY, WTR is equal to 2D plus DOHV, and BTR is equal to DOHV. Next, spacing. Delta H is spacing along height and it is 30 to 60 centimeter. Remember, whenever we are giving some range, take the average value. Delta W is spacing along width and of range 10 to 20 centimeter. Delta B is spacing along breadth and is of range 10 to 20 centimeter. Let us understand dimensions of tank. The total height of tank can be given as height of transformer plus clearance along the height. Width of transformer tank is equal to width of transformer, that is core, plus delta W. Similarly, breadth of tank is equal to breadth of transformer or core plus delta B. Let us understand what are these. Look into this figure. You can see this is nothing but your core and winding, and now it is placed inside a transformer tank. This is your transformer tank. So you can see here the total height of your transformer is HTR, and delta H I have written on the top and on the bottom. That is nothing but clearance. That is the gap between your core and transformer tank. Similarly, delta W is clearance along width, and WTR is nothing but width of your core, including your winding. So now you can see here the total height of transformer tank, that is HT, is equal to HTR plus delta H as given here. Similarly, the total width of transformer tank is nothing but WTR plus delta W as given here. The surface area of transformer tank is given as 2HT into the bracket BT plus WT. Let us try to understand this. Now let us say this is your transformer tank. Remember, your transformer tank dissipates the heat to the surrounding from the side walls. It's not going to dissipate the heat from the top and from the bottom. So out of 6 phases, let us consider only 4 phases through which heat dissipation takes place. So now if you see here, I am calling this surface as the first surface, and here height is HT and width is BT, that is breadth is BT. So the area of this surface is nothing but HT BT. This is the second surface. Here HT is height and WT is your width. So total area here is HT WT. and this is your third surface area, that is HT into BT. And then next, this is your fourth surface area, HT into WT. When you add all these terms, you will get the total surface area as 2HTBT plus 2HTWT. Taking 2HT as common, you will get 2HT into the bracket BT plus WT. Thank you.